This is our video for Unit 6, Day 8. We're going to be looking at today is the graphs of sine, cosine, tangent functions. So we just finished up with a test for the first half of this unit where we're looking at trig equations and trig identities. We're looking at the second half is trig graphs and modeling applications for these functions. So we're going to look at each of the parent functions for sine, cosine, and tangent, and in class tomorrow we're going to review those three functions as well as all the parent functions we've covered so far this year. So first we're going to look at the graph of sine. So anytime we're graphing these trig functions, sine, cosine, and tangent, we always work with a 5-point pattern. And these patterns are different for each function. That's how we graph them to make it simple. For sine, we have 5-point pattern. It was 0, max, 0, min, and 0. When we show you the picture of the graph, we'll show you what this means. So basically, whenever we graph a trig function, we create an axis like this, going longer out to the right and smaller up and down on the y-axis, and we graph one period of the function. So for sine, the largest value sine can be is 1, the smallest it can be is -1. So go ahead and mark those off. Those are max and min, and then we just follow the pattern. So mark off starting at 0, mark off 0, max at 90, 0 at 180, min at 270, and then back to 0 at 360. And that creates our sine curve. So that's the pattern it follows: 0, max, 0, min, and 0. So as we add transformations, I'll move the graph, shift up, down, left, right, reflect over the x-axis, but for a sine function, we'll follow the same pattern, then transform it based on what's in the equation. So these special 5 points we use for sine, we'll also use them for cosine. These are called quadrantal angles. So these are special values for the sine function. So starting off, we start at 0. Sine of 0 is 0. It's where we get our first point in the pattern. And it moves to sine 90. And sine 90 is 1. Then we move to 180. At sine 180, we go back down to 0. Then 270. At 270, we go back down to our min, and then back up to 0 at 360. These angles are called quadrantal angles. These are our special 5 points we graph. These are not ones, values of sine you could find by setting up a right triangle and finding it that way. So these are special angles we call quadrantal angles. So I'm going to put a picture of our sine graph up here again. And let's talk about some properties for the sine function, such as we have for other parent functions. So first we'll look at the domain and range. So for the domain from this graph, it looks like this is the only domain from 0 to 360, but this is only one complete cycle of the function, or this is called as one period of the function. So this wavelength here is called the period of the function. So this pattern will actually continue out to the right and back to the left, so our domain is all real numbers. negative infinity to infinity. But for graphing purposes, we only show one period usually, or two periods, just to get the idea of the function. We don't continue graphing um, either direction. So the range, look at the y values. It goes up as high as 1. It goes down as low as -1. It's bounded. There's an upper and a lower bound for the function. It doesn't ever go above 1 or below -1. So that defines our range. It's always between -1 and +1. So the next thing we talk about for trig functions that repeat with the same pattern, if we talk about the period, that's the length to complete one cycle of the function. So for the sine function, right, we see the whole cycle takes 360 degrees to repeat the whole pattern. Right, and the last property is called amplitude. Right, amplitude basically tells you how steep the sine or cosine wave is, or how much it goes up from the middle or down from the middle. The amplitude for the parent function is 1. So amplitude basically is this steepness here between the midline and the maximum, or the same as the midline and the minimum. Right, you can also find it by taking half of the difference between the maximum and the minimum. So one more thing for vocabulary purposes, this shape that sine, the sine curve makes, and cosine curve also, these are called sinusoids or sinusoidal functions. So like we've seen with our other parent functions, we add transformations of this, which is what we'll do tomorrow. That's going to change some of the features of the function. It's not going to change the domain. We'll always be able to put all real numbers into the sine function, but these range, period, and amplitude will change with transformations. So as we move the function around, that will change our y values, will change the range. We can make the period longer and shorter, um, and we can change the amplitude by adding in a vertical stretch. So the cosine function is going to be very similar to the sine function. The only difference really is it's going to follow a different 5-point pattern. Again, these all come from our quadrantal angles. So we start looking at cosine 0. This is 1. This is the maximum for the function. So cosine starts at the max, moves to the next quadrantal angle, 90. Cosine 90 is 0, so we go from max down to 0. Next, cosine 180, which is -1. That's the minimum for the function. Then next one is 270. Cosine 270, we're back up to 0. And then the last one, cosine 360, finishes off the cycle. We're back up to 1. So back up to a maximum. So this is our 5-point pattern for the cosine function. All right, you'll see that a lot of the properties are the same for cosine as they are for sine. It's really just that pattern that changes. So again, idea for graphing is still the same. We start off with this kind of axis, mark off our maximum and our minimum. We mark off the period, which is going to be the same. Will also be 360 for cosine. And as we add in transformations, you'll see it's going to be each of these special points we mark is exactly 1/4 of the way through the period. So even when we change the period around using transformations, we'll always have one of these marks and follow the pattern by going 1/4 of the way through the period. Alright, then we're going to mark off our 5-point pattern for cosine. It's going to be max, 0, min, 0, and max. So again, we'll look at some of the features for the cosine function. Most of them will be the same as for the sine function. Our domain, same thing. This pattern will continue on either side, out to the left or out to the right. Our domain is all real numbers. The range is the same as for the sine function. All the values for cosine are between -1 and 1. It also has the same amplitude of 1 and period of 360 degrees. Again, for transformations, we're looking at these to change: the range, the amplitude, and the period. The domain will always be all real numbers for these sine and cosine functions. So our last trig function we'll go over is the tangent function. This one's going to be a little bit different because of the nature of the tangent function. So we know from our identities that tangent is the same as sine over cosine. Alright, so thinking back to what we did with rational functions in Math 3, anytime we have a denominator 0, it's going to create a vertical asymptote. So if cosine is 0, the tangent function will have a vertical asymptote. Right, so there'll be some values that are not in the domain for tangent. So that's what we have to exclude. The sine function on top of the rational function, anywhere that's 0 is going to be a 0 for the tangent function. So these will start to form the shape of our graph. There's also one more thing we know from our special right triangles, from the 45, 45, 90 triangle. We know that tangent of 45 is 1. So we're going to use these values. We're going to break up our graph, and we're going to go over the 5-point pattern for tangent. So we'll go out to 360. Where we're going to make jumps for this one every 45. So this pattern for tangent is going to be a little bit different. We know there's going to be a vertical asymptote everywhere cosine is 0. So cosine is 0, we know, at 0 and 270. Sorry, at 90 and 270. So at 90 and 270, we can go ahead and draw vertical asymptotes into the graph. Right, and where sine is 0, we know it's going to be a 0 for tangent. So sine is 0 at 0, is 0 at 180, and it's also 0 at 360. So we can go ahead and put zeros on the graph in all three of those places. Next thing we know is that at 45, it's going to be 1. So we're going to mark off our graph there, and then we'll kind of go through the pattern here one step at a time. So it starts at a 0, goes up to 1, and then we'll continue up along the vertical asymptote. At the next multiple of 45, 135, it's going to be at negative 1. It's going to come up through a 0. At 225, we'll be back up to 1. So go up along this asymptote. And same idea over here, 315 down negative 1, and then coming back up to the 0 at 360. So this picture right here actually shows 2 full cycles of the tangent function. So we see 1 full cycle between the asymptotes, gives you the full pattern. You can also take the pieces of the pattern from either side. Right, we have 2 full cycles of all the values for tangent. So for tangent, our period's actually half that. For sine and cosine, it's 180. For a 5-point pattern for tangent, there's a couple different ways we can do this. We can start at the 0, go up to what we call A, which will be the vertical stretch, and then the next point would be an asymptote. Then our next point across the asymptote would be negative A, so the opposite of whatever our amplitude was, our vertical stretch was, and then back up to a 0 would complete the 5-point pattern. You can also graph between the asymptotes, go asymptote, negative A, 0A, and asymptote. Either way, that gets you 1 full cycle of the tangent function. So our properties for tangent are going to be a little bit different than we had for sine and cosine. So our domain has some restrictions because we have these vertical asymptotes. We see they occur at 90 and 270. They occur all odd multiples of 90. So x can't equal any odd multiple of 90. So the way we write that is 90 times 2k plus 1. Right, 2k plus 1 is just a generic way in math of saying an odd number. If you multiply any number by 2 and add 1, you have an odd number. So that's just a generic way of putting an odd number. So we can't have any odd multiples of 90 in the domain. The range, the tangent function, is not bounded like sine and cosine. So along the asymptote, it'll go down negative infinity and up to infinity. So the range is all real numbers for the tangent function. For tangent, there is no amplitude. You can still have vertical stretch on the graph, but there is no amplitude because there's no bound on the function. It goes no matter what it stretches, it'll go up to infinity and down negative infinity. What does change from sine and cosine is the period for tangent is only 180 degrees. So we'll complete that full 5-point pattern in 180 degrees as opposed to 360. So last thing we have to talk about is the radian measure for angles. As we work through problems in class, we're going to be using both degree and radian measure. So we're going to have to learn how to work with radian angles. So I'll give you some conversions real quick and then kind of show you how to convert from radians into degrees and vice versa. So starting off a full circle in degrees, 360 degrees. For radians, that's 2 pi radians. Right, we can cut both of those in half. 180 degrees, half a circle, would be pi radians. And we can keep cutting in half. Half of 180 would be 90 degrees, would be pi over 2 radians. And we can keep going even there. Half of that would be 45 degrees, would be pi over 4 radians. And these are the most common angles you'll see um, used with the radians will be 45, 90, 180, 360, and then also our 30 and 60 degree angles. So if we want to go from degrees to radians, so say we want to put 30 degrees into radian measure, right, we use this proportion right here to help us convert. 180 degrees is pi radians. So we start with 30 degrees, right, we multiply by pi radians over 180 degrees. I always try and line up our units so one's on top, one's on bottom. We multiply, say we cancel out. So this would be 30 pi over 180 radians. Then we can simplify the fractions. 30 over 180 is 3 over 18 is 1 over 6. So pi over 6 radians, same thing as 30 degrees. And it's the same idea going the other way. If you want to take pi over 3 radians, and put it into degrees, we're going to do the same thing. Pi over 3 radians, multiply 180 degrees for pi radians. That's our radians cancels. We have 180 pi over 3 pi. So if the pi's cancel out and 180 divided by 3 leaves 60 degrees. So this is just a setup. Tomorrow we're going to be working more with transformations. We'll be going through some more properties for sine and cosine. Then we'll do tangents separately. As we work through these problems, a lot of them are going to involve radians instead of degrees, so we're going to have to practice using both measures, radians and degrees for angles. Again, if you're looking for a different video to help you with this, search for sine or cosine graphs on YouTube, and same thing for tangent. And then for radian measure, you can just type in radians to degrees or degrees to radians. There are plenty of videos that show you how to do that.